Hello guys, welcome back to another episode of Intelligence Maxing. So this is day 77 now. Just over 2 months and a half. But I want to spend some time today. Oops. Yeah, that was interesting. Just kidding. Alright, let me see. Okay, I'm popping up on my screen as well. Alright, so I wonder what this looks like then. And I wonder if I can get rid of this. Probably not. Show chat. No. Oh, wait. Pop out, maybe? Okay, it's still the same problem, but I don't mind. There's a few things that I kind of want to go through today. They relate to computer architecture and algorithms, two classes that so far I've been going through a pretty rough patch. It's not easy. I think I got around a 60% on both exams. Class average was around that as well, so I'm doing just about average right now, but want to do better, and I need to figure out best way to do or best way to study. I think I have a decent amount of flashcards here to go over, and then I also have some homeworks and programming assignments that I need to do for those classes. So I think that's probably my goal for today. I want to see if I can stream for a decent chunk of this time. And that being said, let's get into it. Okay, suppose we have a processor that has a 4-way set associative L1 cache. 256 blocks in total. Each block contains 16 bytes. Cache stores 22 bits as a tag and 4 check bits for each block. Hit time to L1 is one cycle. Least recently used policy is used for replacing cache blocks. Okay. Processor has an 8-way set associative 4 megabytes L2 cache, 512 blocks total. So that's a lot more than the 16 bytes here. And the hit time to the L2 cache is 10 cycles. Okay, and the least recently used policy is also used for block replacement. Okay, so this first question is asking us, what is the size of the L1 cache considering the tag and check bits? Okay, so I think some important information here. We're given the 256 blocks in total. So the L1 cache can store 256 blocks, and then each block contains 16 bytes. All right, I think immediately we can take this number and multiply it by this number. So that will give us the total size of the blocks that can be stored in the cache. Okay, so it's 256 blocks and then 16 bytes. So that's the total number of bytes that can be stored within blocks in this cache. The cache also stores 22 bits as a tag and 4 check bits for each block. So if you combine these two, that's 26 bits. And for each block, we have 256 blocks. So we're going to multiply 256 by 26 as well. And then I think we do have to separate the 16 bytes into bits. So we could also multiply this by 8 to get the number of bits in 16 bytes. I think just off the top of my head, 8 times 6, that's 48. So it's 128 bits. Yeah, I don't have the exact answer here, but I'm 99% sure you just multiply each of these numbers together. And that'll give you the number of bits. I guess, yeah, we'll multiply this by this and then add 26 and then multiply the sum of this by that. Okay. Yeah, I need to flag this so I can get the right answer. Well, that's good. Okay, how do you measure speed up? What is Amdahl's law? So speed up, I think, is the idea of, okay, what is your new clock rate divided by your old clock rate? So usually you want a higher clock rate for a faster or sped up processor, and the clock rate for your older or your old processor is going to be less than. So you want to maximize the number of gigahertz or the number of cycles per second. And I think you could think about that then as the new clock speed or new clock rate divided by the old clock rate. Or I think you could do it as the old clock cycle time. So how many times or how many seconds does it take to run a single clock cycle? Divided by the amount of time it takes to run a clock cycle given the new sped up processor. Okay, and then Amdahl's law, I think, it's a equation you could use that mimics this new over old idea, but in this case you're thinking of sort of this parallel or part of a process that can be parallelized or sped up. You could take 1 and you just divide that by 1 minus f plus f divided by s, where f is the portion of your program, your process that can be parallelized or sped up, and then s is the speed up factor. So I think if you were to take s and make that infinity, so that means you've infinitely sped up your process, then I think then the remaining speed up is just the portion that can be parallelized. The portion that cannot be parallelized. Yeah, so you've essentially just abstracted that part away. I think this is what I was referring to. F divided by s, this portion just goes to 0, and you're left with the portion of your process that can't be parallelized. So this is something that you have to run. Okay, I think that's good for now. And how do you find the time it takes to execute one clock cycle? Yeah, this is actually something I do want to get better at because I'm very confused sometimes. What is the unit of 1 gigahertz? So if a CPU's clock speed is 1 gigahertz, does this mean that 1 clock cycle takes 1 nanosecond? Oh, so, okay. Yeah, if you raise this up, then, yeah. So 1 gigahertz is equal to 1 nanosecond, and if you increase that, okay. So it'll be 2 divided by 1 to the billion. Yeah, these conversions are sort of confusing my head. Okay, so you take 1 divided by the I think you just reverse the clock rate, right? So clock rate is, I think, the number of cycles per second. So if you flip that, then it's the number of seconds per clock cycle. And so if, I think if you want to get right, if you want to get the number or one for one clock cycle, you could just do 1 divided by. If it takes 1 second for billion clock cycles, then you divide 1 by a billion. Let me ask ChatGPT. So 3.5 times 10 to the 9. Oops. Okay. PEMDAS. Okay, let's actually make this even easier, right? So if we take 1 divided by 1, that's just 1. 1 divided by 2, that's 1/2. 1 divided by 3 is 0.33. Okay, so that means that this gigahertz, if this increases, then the nanoseconds get smaller. Okay. Okay. I think this is actually, I'm gonna add a flashcard here. And what is the clock speed of 1? Okay. So if the clock speed of a processor is 1 gigahertz, what long does it take to run 1 cycle? Okay, so if the clock speed of 1 gigahertz is equal to, so 1 divided by 1 times 10 raised to the negative 9, right? Okay, and this is going to be equal to 1 divided by 10 to the negative 9. So you have 9 zeros, that's exactly 1 billion. Okay. 1 divided by 1 billion. So it's equal to 1 nanosecond. Yeah. Nanosecond. Okay. A nanosecond, I guess, is a nanosecond a billionth of a second. It's 1 billionth of a second. Okay. Then what is a picosecond? 1 trillionth of a second. Okay, so shoot. I definitely got that wrong on the exam. Ah, shit. Okay. Okay, so that means this would be, if this is 1 nanosecond, then that would be 1,000 picoseconds. Okay, so does that mean 1 nanosecond is 1,000 picoseconds? Okay. So as you're increasing your gigahertz, it gets even smaller. So I think if you have, let's say, a 300 gigahertz processor, I think what you could probably do then is you can pad your number with 2 zeros. So it'll be 0.001 seconds, right? So if you have 1 divided by 1 gigahertz, that's 1 nanosecond. If you had 1 divided by 10 gigahertz, that's 0.1 nanoseconds. If you have 1 divided by 100 gigahertz, that's 0.001 nanoseconds. And if you had 1 divided by 1 divided by, if you have 1,000 gigahertz, that's equal to 1 picosecond. Okay. If the clock speed is 1,000 gigahertz, then the clock cycle time is 1 picosecond, right? Okay. Terahertz. Okay, so let me ask myself this. So what is the clock cycle time of a processor that has a clock speed of 100 gigahertz? So the clock cycle time would be I actually like the way that ChatGPT broke it down. So it'll be 100 times 10, right, raised to the -9, so it's a billion, which is equal to, so we have a billion, 100.001, nanoseconds. Sorry, it would be 0.01 nanoseconds. If, yeah. These zeros are a bit confusing, but because if we divide this by 10 gigahertz, gigahertz, 1,000 gigahertz. Okay. For 100 gigahertz, clock cycle time would be, okay, so for 10 gigahertz, clock cycle time would be okay, and this would be 0.1 nanoseconds. So for 1,000 gigahertz, the clock cycle time would be, and then this is where we could put this, and this would be 1,000 times, which is equal to 0.01001 nanoseconds, which is also equal to 1, and this would be 1 picosecond. Okay. Yep. Alright, so then 100 gigahertz would equal 0.01. Okay, nice. Just want to make sure. Shout out ChatGPT. Alright. So that's actually a very helpful flashcard to add. Can get me more comfortable with. Oh shoot, did it get added? Okay, nice. Alright, let's go through the ideas again. So initiation interval. I think this is if you have some type of pipeline system. How many cycles do you need to wait before you can start executing or fetching the next instruction? And that next instruction is the same as the previous instruction. Is a unit, is the idea of how many cycles does a unit need to wait until I can execute? Let me ask. Is the idea of an init interval the number of cycles a unit needs to wait till it can execute the same / similar instruction? Okay, so controls the throughput. So how does the idea of a pipeline architecture come into play? So if an instruction can always be pipelined, will it have an interval of 1? I feel like that should be the case, right? Fully pipelined. In a fully pipelined architecture, no stall, no dependencies. The init interval of all instructions instructions will be 1. Okay. Okay. In this case, what is the average memory access time? So assume the same loop execution the question above, but this time the processor accessed the following memory address in the sequence in every iteration. Okay, so I think this is asking us really, we have a cache, and in this case, we should really be converting these into binary numbers and figure out what the index bits, what the tag bits is going to be. Yeah, so I think we're missing some information here because we don't know how many bits are within the index bit. We don't have really any good information to figure that out. It would be nice if we had the block size. Then we could figure out the offset bits. And then maybe the set associativity of this cache. So I think I'm going to skip this for now. Okay, I remember I did write something. I think the idea was that you have 5 instructions, but in the question we were given a 4-way set associative cache, and all of them eventually did have the same index bit. So each time you go through it, you're always going to have a cache miss, and I think then the average memory access time was going to be the miss penalty 100% of the time. Hit rate. So hit rate is the idea of, okay, if you're accessing your cache, how many times are those going to be actual hits, or cache hits? So how many times will that piece of data you're looking for actually exist in your cache? Okay. Suppose we have a processor that is 4-way set associative. Okay, this is, yeah, similar before. Oh, shoot, I accidentally pressed. It's okay. How do you find the time it takes to execute 1 clock cycle? Okay, so we had talked about you just need to reverse or invert the gigahertz unit, right? So you have, in the case of gigahertz, it's cycles per second, but what you're finding is the clock cycle time. So the time it takes to execute 1 cycle, and this is really the cycles per second. Sorry, seconds per cycle. And what you have to do is just take 1 and you divide it by the gigahertz, right? 0.5. .35 nanoseconds. Okay. Instructions per cycle. I think this is another ratio measure of performance. You take the number of instructions that you've executed, and then you also divide that by the number of cycles that have passed. There's also the idea of cycles per instruction, so I think it's just the inverse of that. Yeah, so is instructions per cycle, you could do equal to total instructions divided by total cycles. Okay, yeah, the higher the better, that makes sense, right? Okay, so IPC is equal to have a fraction, and in our fraction we have the total number of cycles, total number of instructions, no, instructions and total num cycles. Okay. Oh. My best video yet. I just posted on YouTube. Go check it out. Okay. Let me see actually how is this stream doing? Okay, we have no one watching. That is perfect. Okay. This means we can execute more instructions per clock cycle. Okay, so cycles per instruction, and that means we want that to be as low as possible. Does a higher IPC results in a better performing CPU? I think so, right? Okay, so thus a low CPI is good for performance. Okay. G equals greater efficiency, right? Is the clock speed of a processor, the clock speed of a processor is 1 gigahertz, how long does it take to run one clock cycle? I think the idea here is we talked about one gigahertz is you're taking 1 billion cycles per second. Are you able to run 1 billion cycles per second? And that means that if you want to run one clock cycle, that's 1 divided by a billion. So that's 1 nanosecond. Second. The clock cycle time of a processor, there's a clock speed of 10 gigahertz, 100 gigahertz, 1000 gigahertz. So I think that steps down to 0.1 nanoseconds, 0.01 nanoseconds, and then 1 picosecond, which is also the same as 0.001. So 1,000th of a nanosecond. Yeah. 10th of a nanosecond, 100th of a nanosecond, and then 1,000th of a nanosecond. Okay. Okay, in this case, why can add.d and s.d overlap with overlapping clock cycles? Okay. Right. I think this is talking about this part. So this is, I think, an example of a pipeline table chart, or pipeline time tabling chart, where you can see here that this add instruction is being fetched in cycle 7, but then in its decode phase, this is a 5-stage process where you have your fetch, your decode, your execute, your memory store, and then I want to say this is memory. I forgot what this last one is. I think this might be register, write to register, and then write to memory. Okay. So your register becomes available on the 4th stage, but the memory becomes available on the 5th stage. Okay, so this stalls here 8:35 in the decode phase. I'd imagine probably because it relies on something from the previous instruction, or the previous instruction is still executing using the fp_add functional unit, so the floating point add, and this just has to wait until that finishes. So that's why you see the stall here. And then after the 35th clock cycle, then on the 36th, that's when this add instruction can start executing. And it seems like it'll take 5 clock cycles to finish. And then it just goes to the write to register and then also the write to memory. Okay, so in this case then, you also have this store floating point instruction here, and it does have to stall because this instruction has stalled in the decode phase. So you really can't do anything until this finishes stalling, and then you can move on to the decode phase. So I think that's why you stay from 8 to 35. Okay, and then once this decode phase happens, you notice here that we don't have to stall because this is executing. We're using 2 different functional units here, and so this store double word, so I don't think it's a double word, I think this is just a floating point word or number. Then we can continue going through the execution phase, and then at the end here, you'll see that this actually finishes before this add instruction, even though the store instruction comes after it in the instruction list. So I think this means that it's an out of order pipeline, so you can have instructions that come after it, execute, and finish before the previous instructions. So I definitely got this wrong. I screwed this up in the homework. Okay. What is the idea of an inits interval? How does the idea of a pipeline architecture come into play? So the initialization interval is how many clock cycles does it take for you or for some type of system to run the next instruction that's the same exact instruction. And then I think the idea of a pipeline architecture comes into play because if your architecture is fully pipelined, that means there's no stalls, I think no dependencies, then you just have an initialization interval of 1. Yeah, that means you can just start your next instruction in the next clock cycle. How many times does a unit need to wait? The next clock cycle. Okay, save that for now. Say it's good. Okay, this one is, yeah. What does instruction 7 stall in the fetch phase? Okay, I think that's what we had talked about earlier, where we can't have 2 instructions in the decode phase at the same time. And so because add instruction is stalled in the decode phase, the store instruction needs to stall in the fetch phase before it can move on. And you'll see this actually repeat here where you have this add instruction that stalls in the decode phase, and then this XOR instruction that stalls in the fetch phase because it still can't move past that. What is the difference between multi-core and functional units? I feel like there are two different ideas, right? So multi-core is the idea of you have some type of processor and you have multiple cores on that processor. And I think a core is actually just composed of functional units. So you have a functional unit that could be a circuit built to do integer addition. You also have maybe a floating point addition or division functional unit. ALU in a core of a CPU. Okay, yeah, that's actually. Cores are composed of functional units. Okay, so the relationship between the two are that cores are actually composed. So cores are composed of functional units. That's important. Okay. All right. So I think we've been. I want to say we've been streaming for a decent bit now. So 40 minutes. That's not terrible. Okay. Are branch instructions I-types? Yeah, I think so. It says right here, but I think this is actually where the address of, or the location of the instruction that we jump to, that's where this is stored. Okay. How do you find the tag bits of a memory instruction? I think it should be of a memory address, not necessarily an instruction. So I think each memory address is built or split up into your tag, index, and offset. I want to say the tag and index are sort of the idea of a cache address. It's kind of like your city and state. I would say probably the state is your index and then the tag is your city. Okay, so the tag bits of a memory instruction, you can find the offset bits if you have the number of, or the size of each block. You can find the index bits by taking the total number of blocks that you have and dividing that by the set associativity in your cache. And then the tag bits, you could just take the total size of your memory address and then you subtract that by the size of your index bits and then you subtract that by the size of your offset bits. Okay. So what is I'm gonna see if cache is a cache memory address a thing in computer science? There we go. Okay, say this is hard for now. Get back to it. I'm gonna take a break real quick, go use the bathroom. Get some stretching in, maybe some sit-ups. Ooh, fix my posture. Okay, I'll be back. Gonna get a magazine. Some go sit on the toilet. Dreams from the future. Alright, I'm back. So I got myself some coconut water. Tastes good. Okay. There's a fly. Shoot. Maybe I'll get it later. I don't know. I'll get it later. Okay, I'm back. Alright. So if a clock speed of a processor is 1 gigahertz, how long does it take to run one clock cycle? That would be 1 nanosecond, because we take 1 divided by 1 billion, convert that into seconds, that gives us 1 nanosecond. Okay. Instructions per cycle is how many instructions can you execute per cycle? I guess you could think of it as an average almost, and the higher the better. The higher this number is, that means the more instructions we can run per single clock cycle, so it's more efficient. And just think about it as total number of clock cycles. Sorry, total number of instructions divided by total number of cycles. Okay. What is the clock cycle time of a processor? That's 10 gigahertz, 100 gigahertz, and 1000 gigahertz. So I think that's 10 gigahertz will give us 0.1 nanoseconds, 100 gigahertz, 0.01 nanoseconds, and then 1000 gigahertz is 0.001 nanoseconds. Just 1 picosecond, okay. Nice. Okay, in this case study, y can add that d and add and s dot d overlap within overlapping clock cycles. Okay, we had talked about they're using different functional units, so their execution time can overlap. Branch instructions are I-type instructions. Okay, I'm gonna skip this. Instruction 7 stalls during the fetch phase. Yes, it does, because of the fact that add.d is stuck in the decode phase. Okay. Difference multi-core. Okay, so multi-core refers to the idea of you have some type of core, or I guess multiple cores on a CPU, and actually it's each core that is composed of different functional units that could be used for addition, division, multiplication, subtraction, for integers, floating point numbers, whatever it may be. Okay. If a company has 10,000 computers, each with a mean time to failure of 35 days, and experiences catastrophic failure only if a third of the computers fail, what is the mean time to failure of the system? So I think in this case, the company has 10,000 computers, each with a mean time to failure of 35 days. Okay, so I don't know the exact way to calculate this, but let's try to use some critical thinking. You have 10,000 computers, right? The mean time to failure of a single computer is 35 days. You can maybe take 10,000, divide that by 35, right? So what is that going to give you? I think that'll give you the average number of computers that will fail per day. And then what you could do is 10,000 divided by 35. That's maybe somewhere along the lines of 300. And 300 times 10 to get to a third of the computers. So it's like around 3,000. So maybe somewhere around like 10 to a few more days. Okay, 11.67 days. I think I was on the right track here, right? 1 divided by 35. So I was slightly overestimated. Said 300 instead of 285. The mean time to failure of one computer in the system is 0.0035. Okay. So we really didn't even need 4 here, right? Okay, I'd say it's hard but doable. Virtual memory. The idea of virtual memory is the way that programs are stored in physical memory can be difficult without the idea of virtual memory. Because I think the optimal way to store data is by having it in a contiguous block of memory so that the program that you're running can just start from the beginning and just offset itself, besides having to store 2 locations of memory. So that's the idea of virtual memory. You have a block of virtual memory that's saved for any process you're running. And this way, you could store a single contiguous block of memory for your process, and then this contiguous block of memory will then map to different parts of your physical memory address. And I think then in that case, you have a physical memory, a virtual address table stored in physical memory in order to look up the actual virtual memory addresses in your computer. Okay, multiple programs active at the same time. Space from a disk, source device, side RAM. Okay, that's good. So a page is the idea of, it's like a block essentially. Like a block in your cache, it's just a piece or part of your virtual memory set. Or maybe a piece of the fixed amount of memory that is given to this virtual address space. So a page is a single sort of block within that. In virtual memory. Because I think the physical memory is called a frame. I think the CPU determines the page size, right? CPU and operating system. Okay. So how do you tell? Interesting. Alright, so what if I just do that real quick? Oh, 2 views. Nice. Alright, terminal. Get conf. Okay, so this is in bytes. How do I, okay. If I want to get this in KB, I can do Python 3 real quick. 16384. We divide this by let's divide this by 1024, so that's the number. So it's 16 KB. Okay, 16 KB. $16 kilobytes for the page size on my Mac. Okay, that's cool. Get conf. Wait, what does get conf do? Help. Oh wait. Path name system var. /proc/mem-info. Okay, yeah, I don't know. That's cool though, that's cool. Send pics. Okay, so determine the bit size of a memory address in hex. I think you just take each hex digit represents 4 bits. So you just take the number of hex digits. There's 6 here, and you multiply that by 4, so that just gives you 26 bits. Okay. So this is the mean time to failure. All right, well, I think this is actually a good stopping point for the flashcards. I think it'll be probably pretty valuable if I went through some examples and go through some practice problems and maybe finish up my homework. I'll probably spend the next hour going through some practice problems and then going through the homework, and then probably then projects as well. So if I could spend next hour doing practice problems, looking through the lectures. Okay, so I think, I'm not too sure if I could share this stuff on my computer. So I'm just gonna block it out for now. Oh, well, I just realized you guys can't even see. My computer screen froze. That is unfortunate. Well, I blocked everything out. Okay. Logging into my account. I wonder if it's gonna make me call. No, it's not. All right. No, it is not. Okay, let's go to CMSC 411. I'm also very curious if someone responded. On the Piazza. No, shoot. practice set question 5. Okay, so this is actually very interesting. I think that these problems should be pretty virtual memory. I think these are going to be some interesting problems. So this caching TLB, yeah, that's something I'm going to have to look into. Okay, so these are all virtual memory questions. All right, let me see if I can get rid of this. All right, so in this case, consider a virtual memory system with the following properties. We have a 48-bit virtual address space and a 32-bit physical address space. So 4 gigabytes and 16 kilobyte pages. What is the total size of the page table in bits for each process on this machine, assuming that the valid protection, dirty, and used bits take a full total of 4 bits being used? So I'd imagine then all of the pages okay, so we have 48-bit virtual address space, right? Important information given to us, okay? So 48-bit virtual address space and 2 16 KB pages. We can find the number of bits used to store the virtual page number. Okay, using what we already using we might not even need the 32-bit physical address for this problem. Okay. Virtual of the VPN and offset. Okay, that means the offset can be calculated as we'll do log base 2 of page size. Okay. Okay, so this means that offset can be calculated as log base 2 page size. Okay, so answer bits is equal to log base 2 of 16 KB which is equal to log base 2 of 2 to the 4 times 2 to the 10, which is just equal to 14 bits. All right, and that means the tag bits, sorry, not the tag, VPN bits is equal to, we're given a 48-bit virtual address space, and we just want to subtract 14, which is then going to be equal to 34, right? Okay, yeah, 34 bits. All right. So we add 4 gets 38, we add 10, it's a 48. Okay, so we have the number of VPN bits. So 34 bits. Okay. So this means that the virtual page table, what does it store, right? So page table stores VPN. It also stores control bits. So this is the valid, protection, dirty, and use. And then also the physical frame number, right? Physical frame number is find the number of VPNs, find the number Okay, so find the number of bits. Using find number of bits of PFN. Yeah, this one's a bit hard. I'm gonna so text PFN is equal to, okay, we actually do need the physical address space. 32-bit physical address. Okay, so PFN bits is equal to 32, and we subtract the offset, which is the same. This will give us 18 bits. Okay, so we have 34 bits, 18 bits, and then we also have control bits. So 4 bits. Well, let's say this is given in problem. I don't know, at this point, this is where I'm not entirely sure. Do we just add up all of these together? So 34 times plus 34 plus 18 plus 4, or do we take this, raise it to 2 to the 34, for each process in this on this machine? Okay, so I think we could probably just add everything up. To find add up to find the size page table for each process. Okay, I feel like that's the key, right? Each process. Okay, so it's like a single program that it'll need 34 plus 18 plus 4, which is equal to 22 plus 34, that's 56 bits. Okay, I'll save this for now. Going to probably need to come back to that, but let's see the other question, right? An approach to deal with the problem that arises from a larger number of virtual pages. Store only a single page table entry per physical frame. Oh, okay, so table is indexed with the physical frame number. Okay, so we had computed above the physical frame number was, I think 18 bits, right? I'm gonna actually see if I can, I might have to delete this. Oh shoot. Oh, here we go. Answer this question. So what do we need in previous questions given? All right, virtual address space is equal to, I think it was 48 bits, and then physical address space is equal to 32 bits, and we're at the, so I see that this is a problem because we do have a higher number of bits for the virtual page numbers compared to the physical addresses that we actually have. Okay, and then I think finally we got a page size, which is equal to 16 KB, right? Okay, so I think maybe this is, you just need to add some stuff together. let's, from the previous question, let's just add what we've learned, right? So the BPN bits is equal to all right, we had taken 16, it's 2 to the 4, 2 to the 10, so that's 2 to the 14. 14 minus 48, so that was 34 bits. And PFN, so physical frame number of bits, is equal to 18 bits, right? Okay. I wonder if we can just add everything here again too. So answer, add up all of the bits. So we have 34 plus 18. I don't think we need the offset, right? So 34 plus 18 plus 4. And we also need to add 10, which is equal to 66 bits. Okay, what I might think we also could need to do is we need to multiply this by 2 to the 18 if each entry, like, okay, so this is the row, right? How many rows? So each row is going to take 66 bits. But how many rows do we actually have? I think we would need to multiply that by 2 to the 18. So I'm gonna to find the size of each entry and then multiply by the number of entries. Okay, I think what we could do here is we take 66 bits and then we just multiply times 2 to the 18. Total size of inverted page table, and so that's going to be equal to 66 bits times 2 to the 18. All right. So the virtual memory system is implemented with a 2-way set associative TLB with a total. Okay, I don't know what a TLB is, to be honest. Okay, so what is a TLB? translation look-aside buffer. Okay, interesting. So a TLB is just like a cache, then it seems like, but for virtual addresses. Okay. So TLBs are caches, but for virtual address. So that's good to know. Just doing some quick cleaning up. Oops. I bought some in trash bags. Oh, here they are. Here they are. Alright. I made it. I made it. Okay. Let's get back into the groove of things. Just a 5-minute break. Two-way set associative TLB translation look-aside buffer, so it's a specialized cache. In this case, we're given the problem virtual memory system, a two-way set associative translation look-aside buffer with a total of 256 entries, 128 sets. Okay. So there's 256 blocks. 28 sets. Describe the virtual memory address organization. Okay, so we're gonna have to do some drawing here. Maybe we could use Excalidraw. Excalidraw. Okay, so let's first describe so this could be our page lookup table. And I want to say page lookup table really has, three things we need. I don't know, this is maybe, okay, so it has three things. So the first is the virtual page number. And then we also have, I guess this is continuing from the other problem. So we have our virtual page number. And a physical page number. Then we also have our control bits in the middle. Let's do that. Control bits. And then virtual page number. Okay. And then this is going to be our physical frame number, PFN, right? So, and then this will be our page lookup table. Yeah, this is probably not drawn to scale because I think our physical frame number and our virtual page number is going to be a bit bigger. So let's do this. This is our page lookup table. And in this case, we have a transaction or translation look-aside buffer. So I think then we can create another table here. So this will be our TLB. TLB is our translation look-aside buffer. I think that's what it's called. I have to double check, but we take this and I feel like this is probably going to be the same as just any regular cache. We have, in this case, two sets. So we could have our index. Okay, wait. Let's just split this down the middle first. So we have set one, and set two. Right. Okay, and then in each set we have our index, so our set number. Okay, so our set number. And then I guess this could be our tag. Do we need a tag in the TLB? Let's see. Okay, actually let's break down. So we have, let's imagine this is our virtual address. So this is our virtual address. Split this down the middle. Let's split this over here. So this is going to be the virtual page number. This will be our offset. Okay, so this is our offset. All right. And then let's bring this over here. So we have our virtual address. So, oh, wait a minute. There we go. Okay. Oh. Oh god, okay. So physical address. So physical frame number. And then we also have an offset here. So I'd imagine we have the set number here. Maybe the value here would then be so this is, we'll call this the VPN. So we access the cache through the set number, and then we grab the virtual page number, and this will link us to this virtual page number here on the page lookup table. And then once we look up the page number here, then this will translate to a physical frame number. So if we have this side by side, then maybe this will be better. Is there a way we can curve this? Oh, we can curve it, all right. Okay, I'm gonna leave this for now. The figure should show the bits for various fields of the virtual address. Right, so this is gonna be, ooh, I wonder if you can create like a, wait. So this will be 128 set, and let's rotate this 90 degrees. And then this virtual page number, so the set number, all right, what's the cache address? I actually don't know what that number could be. Okay. So this should be our cache address. We want offset. I'd imagine we get like a index number, and then maybe a tag as well. Yeah, I don't know, because I have to think the offset here represents the block, but I don't know how big is a block in this case. Oh, well, okay. They actually give it to us. So there's 256 entries. So there's 256 blocks, right? And then there's two sets here, sets 1, sets 2. Okay. So if that's the case, then we know there's 128 sets, so that means the index has to be log of 2 to the 7, right? So that would be 7 bits in the index. We're not given how... Cache address index bits, that is going to be equal to log of num sets, which is equal to log of 128, which is equal to 7 bits. Okay. How do I move? Oh, there we go. Okay, so 7 bits. Is the offset the same though? I don't know. Because I don't think this is storing actual data in the cache. I think this is just storing the virtual page number. And virtual page number we actually did get. I think it was 34 bits, right? Okay, I'll leave this here for now. I think that this is maybe a good stopping point for this question. I'll come back to it, Okay, I'll just add that and then get back to it. The page table. The second table in the question is the page table. The virtual page and table is invalid present. The frame number will be determined at runtime. Okay, so I guess this is, we have to fill this out here. It's the page table. So this virtual page number is invalid present and means that the page should be loaded into a physical frame in memory when it is accessed. Okay. That's where this comes from. It means that the page should be loaded into a physical frame in memory when it is accessed. Okay. Frame number will be determined at runtime. However, for simplicity, assume that the physical frame number already given, physical frame that is loaded. Okay. Guess that's the same here. Okay. Page table, hit, or false. Yeah, I wonder what this is. Okay, so I notice here that entry valid, this 0 represents the virtual page number here, but it doesn't have the same physical page number as this. I'd imagine that this is probably our cache. And this is our virtual page table, our page table. So maybe these numbers are just filler numbers, but let's try to run through it based on what we know. So running through the sample, we have virtual page accessed VPN virtual page is equal to 1. So TLB, it is going to be a miss. TLB miss, and page table is equal to miss, fault. Okay, so that means this then becomes, if we just fill this out, do we just virtual page access is equal to 5, right? And then I feel like we should be giving a policy of how we could update our cache if this is our cache. But let's say TLB is equal to hit, PT is equal to, so page table is equal to hits. Yeah, if this is it, I don't want to go through all of this because it seems pretty manual. So I'm just going to add this for now and come back to it. Also, I think UFC is about to start. I'm kind of curious. Okay, I guess they're about to start this soon. Can't wait for, honestly, all of these fights seem very exciting. Okay, virtual memory. Suppose the matrix of size 16K. 16K rows in 8 columns of chart data elements are stored in virtual memory in row major order. No elements was added to the memory before the code is executed at the first byte of a page. Okay, row major order, I'm going to assume is that you have 16 rows, 16K rows, so you have a matrix which is a square. You just go row by row by row, and virtual memory is really a line of numbers, so I think it's going to be row by row, and that's just going to create a big line. Yeah, that's maybe a bit confusing. Ooh, Allison is in New York right now. Damn, this pizza looks good. Also, the sushi. Oh, God. My mouth is watering. All right. Huh, hood looks kind of weird. All right, I'm getting distracted on my phone. I'm getting distracted on my phone. Okay, so row major order is equal to storing row data in virtual memory space. So 4K 4x24 page faults. Okay, page fault I have to remember. So I think then each row is 8K. Each row is 8K memory. So the number of bits used for page offset, that's actually found by the page size. So if we can find the page size, background, helpful notes, okay. page off, number of bits used for page offset is equal to number of bits used, is equal to log of page size. We can try to find page size to get the answer, to get the final answer. Okay. Number of bits used for page offset is equal to page size. Oops. Trying to think. If number of bits used for page offset, so how do we find the page size here? Well, we're given that matrix has size 18K by 8K. Maybe we could find the page faults. Because maybe it's initially how this might work is our virtual memory address space is essentially empty, and every time we store something, yeah, I'm not entirely sure. Maybe we could take this 4K here, we multiply these two together, divide that by 4K. Yeah, it would be very helpful to know what the units of page faults are. Page faults is equal to, let's see. Oops, okay, so does a page fault occur when a program runs for the first time? Okay, so program tries to access part of memory that is not located in the system's physical memory, so RAM. So a page. So I think, yeah, at first, through every single iteration, there is going to be Okay, so answer. During the first when the program is first run, there will always be page faults because the pages haven't been loaded into, haven't been mapped to a system's physical memory yet. Okay. Executed. Faults. For 4K in this situation, meaning that the okay, so let's do 16 times 8, that is 128k squared. Right, and then we divide by 4k, so 4k, 128 divided by 4, was it 8? Yeah, 8k times 16k. Right. The total size of each page then is 128k squared divided by 4k, which is equal to, is this divided by 4? Is this divisible by 4? It should be. Okay, so we have 30. 4 times 30 is 120. So 32. There's 32k. So this means that they're 32k. So finding the number of bits then is equal to 32. So log base 2 of 32. So it'll be 2 to the 5th times 2 to the, we'll call it, I think 10, right? Which is equal to 15 bits. For the page offset is then, okay, let's go. I'm gonna put that there for now. So it's the same, wait. Oh, they just swapped it around. Maybe then this code has something to do. So now this is column, it seems like column major ordering. Because you're not iterating through the columns, you're iterating through the rows first. Or, I wouldn't say first, because this comes in the first of for loop, but you're actually iterating through the columns. Okay. Iterating through the rows, it's confusing, sorry. How many pages? This is actually decently long. All right. I think I should probably check my work soon after this question. Let's see if we're on the right track. Okay, so assuming the page size computed from the previous question, I think we saw that was 32K, right? I feel like this one, wouldn't this be the same? Like, should it not be the same exact page size number? We completely ignored the chart. Yeah, this one is hard. I'd imagine it would just be the same, like the same page size, but I have a feeling it's not the answer. Number page faults, right? Wait, let me think. Yeah, I don't know. I'm not entirely sure about this one. Okay, so I think that's kind of good for now. I'm gonna take a quick brain break. Okay. Yeah, let's see. How is the stream health doing? It's been 2 hours, not bad. 2 hours of decently hard work. Okay. All right. Transporting a bunch of stuff. Let's see. Into my closet. Oops. Maybe this clock could be useful. Just don't know where to plug it in. Got a lot of these wires though. Okay, let's see if this fits in my desk. Oh, nice. It does. Oh. And the timing isn't off by that much, actually. Let's go. Okay. Cause it's everybody when we inside. AI Energy Summit. Okay, my room does look a lot more clean. Now, I think it is time. Let's go take a look at some of these solutions, see if we're actually on the right track. Okay. Gonna pull this one up. Just to block this real quick. All right, let's see. I think this one, right? Question 1. Consider a virtual memory system. Okay, so I definitely got this wrong. For each process on so number of page entries, virtual address space divided by page size. Okay, yeah, 2 to the 34, so this will be 34 bits. Number of physical pages is equal to 18, right? So this is going to be our offset. 18 bits to represent each physical page number. Okay, so size of each page table entry, so 18 plus 24. Okay, so each page table entry then only stores the number of bits for the physical and the valid bits. Okay. Number of entries for virtual page table. So then this means number of virtual page table entries. So this is going to be equal to 2 raised to the 34. Okay. 18 bits. Okay. So find the number of bits per entry on the page table. So this would just be bits per entry. So this is equal to physical frame number bits. Then we add control / other bits, which is equal to 18 plus 4, which is equal to 22. Okay, and then finally we just multiply the number of bits per entry. Okay, multiply the bits per entry by the number of entries to get the table size. Okay, so this is table size is equal to text bits per entry times num entries, which is equal to 32. Oh no, it'd be 22. And then we multiply this by 2 raised to the 34, right? Which is right here. Okay. So it only stores control bits and PFN. Total size, assuming that I guess each process, it's not, a single entry doesn't represent a process. A single entry represents a page, right? So we have to find the number of entries times size of entry. Okay, curious what is going on with the UFC. Okay, so this happened 32 minutes ago. Twitter. Okay, wow. It's coming soon. This one's coming soon. Okay. All right. Were we able to understand how this question works now? So if we're asked to find the total size of a page table in bits, okay, we're given the offset. No, we're not given the offset. Well, we are given the size of each page, which is 16 kilobytes, right? And then we could break this down into 2 to the 4 times 2 to the 10, and this gives us 14 bits. Then we have the number of page table entries, so that we actually need to find the number of bits used for the virtual page numbers, which is going to be 34, and then we raise 2 to the 34. So that's the number of entries that we have in our table. And then what's actually stored within this table is going to be the physical frame number, which is going to be an 18-bit sequence, 32 minus 14. The offset here is the same as the offset in the virtual page, because I think the physical frame and the virtual page, they should be the same exact size. So if you have a virtual page that is 16 kilobytes, then our frame is also going to be 16 kilobytes. Okay, so we have 18 bits for that, and then 4 bits for control bits or other bits, which is given in the problem. So we found the number of bits per entry on the page table, which is going to be the physical frame number bits plus control and other bits, which is equal to 18 plus 4. That gives us 22. And then we multiply the bits per entry by the number of entries to get the table size. Okay, that's good, that's good. All right, so question, did we skip C? Okay, I think we did. So, oof. So they have 34, which is the virtual page number of bits. They don't add physical frame number bits. Yeah, I'm gonna be honest. I have no idea where they're getting this divided by 8. Okay, this makes sense since we do have to multiply by 2 to the 18. Because this is the number of entries that we have. Okay, so we don't actually add the bits here. Oh, okay. They divided to get the bytes. I just added, okay, I think I added something. I just added the PFN bits when I shouldn't have to this. Okay, so this should give us then 48 bits. Size of each entry, so this is equal to 34, okay. Size of each entry, and then this is really going to be equal to times number of entries, which is equal to 48 bits times 2 to the 18, okay. In the inverted page table, okay. Note that the size, the entry does not include bits for the indexing column. Okay. So I always got confused. I always added the bits to represent the index, but it seems like you don't need that. It's 32K. After loading a page, all elements will be accessed until the next page fault. So I think I was right. It was just the number of page faults. In this case, 4K. Okay. Yeah. Okay, this is crazy. I might have to understand that one a bit more. Okay. But let's go to, I think, question C. Right. So it's this one, virtual memory. Okay. Okay. It seems like. Oh, are these two different sets right here? So you get the page offset. What is VDPU? And why is this split up into two different? Oh, the valid dirty. Okay. Shouldn't that be 4 bits? In this case, it seems like it's 6. Oh, okay. This actually might be 27. So this is the tag, and then this is the index. Okay, this is the page offset. I wonder what do you call this? Like a cache address? So offset is the same then as before. You just store that. No, that's not stored in the cache. Okay. It's almost been 3 hours, not bad. Almost been 3 hours. Okay. I'm getting distracted. Still getting distracted. Oh wow, just finished. Okay. Dan Yuge. Was it unanimous? Probably not if Dan Yuge got. Right. Unless that means that Dan Ige got knocked down. Not sure. Right, I'm gonna UFC Twitter.
Lerone, the Miracle
No. Sucks to see him lose. Yeah. This guy has never been knocked out, which is crazy. Oh man, I'm excited. I'm excited for this. Bryce Mitchell. Yeah, I mean, Ilya has just cleared through this. Very interesting, Max Holloway. An absolute dog. All right. Going back to the Discord. Yeah. I think after this, what am I gonna do? I might need to go through the homework from my algorithms class and then come back to this. Right now it's 3:20, so okay. Alright, but yeah, let's try to figure this out. So, cache address. I'm gonna zoom in a bit here and give this down here. So this should be 14 bits. So index we had computed, it was going to be, actually we could put it down here, be 7 bits. Right, how do we know? So cache address would be 48 bits, right? Okay. And the reason maybe why this is 48 bits is because of we're given a 48-bit virtual address space. Okay. So I guess the address is the same. So you have a memory address, it's 48 bits, but the way the cache interprets that address is a bit different. Okay. So virtual address is also 48 bits, right? And this will be 14 bits for the offset, and this itself would be 14 bits, so this will be 34 bits. Okay. Okay, okay. Oops. Okay, physical address, physical frame number. Alright. The question is, okay, so physical address, this is 32 bits, which is given in the problem. Okay, and this must mean that the offset is the same, but this number changes, so this is going to be 18 bits. So we have 18 bits for the frame number. Okay. And then we need to find a way to map this 48-bit cache address over to a 32-bit physical address. All right. So how do we actually go about doing that is a good question to ask. This is where the TLB, the translation lookup table, or look aside table, I forgot what it is, but we have two sets, so set 1 and set 2. Maybe we don't even need to worry about the tag and physical number. Okay, so let's get rid of this then. So we don't even need the page lookup table, but what we do need is this translation look aside buffer, which probably is wrong. Okay, so let's just create two of these then. We'll call this set 1, and then we'll call this one set 2, right? Okay, and then we need a tag. So other bits, right? And then we have our tag and physical PFN number. So PFN, physical frame number. Yep. Okay. All right, let's take this. Just bring this over to the side. Okay, now that we have this broken down, this should be cache address, and then our physical address. We can make a line from the offset to offset. So the offset is the same, but the index will bring us to this side. Right, and then our tag this could also bring us to this side if we want. But then the tag will and then this will bring us to this. I could probably just go straight through it. So this then would be 128, so 128 bits, no, 128 sets, yeah, sets. And then each of these sets, so we have other bits, tag, and PFN. So this will be 27 plus 18 plus 4. It does the cache, okay. Does cache store index bits? Does a TLB store index bits? Okay, maybe this is actually a question I might ask Piazza. Yeah, I'm gonna ask some of my TAs about this real quick on Piazza. wait a minute. Wait. Does a lookup table store the page number? PFN. Okay, so I think this should be okay. Because I think in their solution, they decided to combine the tag and virtual page number into two different. So this is the index, this is the tag. I think they decided to combine it into the tag. Oh. It's like 1, 2, 3, 4, 5. 6, 7, okay. Yes, this is an example of an entry, but the actual set itself should contain a sort of index thing. Okay. So it'd be 34 bits for the tag and index, 18 bits for yeah, 18 bits for the physical frame number, 27 bits for the tag, 4 bits for the other, and then 7 bits for the index. Okay. Okay. So I'm gonna add this. Oops. I wonder if I could copy clipboard as PNG. That each set is yeah, I want to call this set 1 actually. Maybe I would call this group 1, group 2, 2, ESPNG. Each group is 128 sets by, so other bits 4 plus 7 plus 27 plus 18 bits long. So 4 is equal to other bits, 7 is equal to index bits, 27 is equal to tag bits, and then 18 is equal to PFN bits. Okay. I will leave that there. And I think this is a good stopping point for, I totally forgot to add it. But I think this is a good stopping point for this class right now. I want to start working on my algorithms class homework. Let me see what's going on with the UFC though. Gets it starting. That's crazy. Okay. Wait a minute. Alexander Rasik. Oh, latest maybe. UFC 308. Okay, so it seems like Alexander Rasik record. No, yeah. Yawn. 2 split decision losses. That's unfortunate. Okay, next is Comsat. Comsat's coming up. It should be interesting. Okay. I don't know. Should I continue streaming here? We've hit the 3-hour mark. Maybe I'll go take a break, eat something, and then come back to it. And maybe I'll go to the library. What can I eat today? Dining hall food. I could eat some dining hall food for dinner. And in the meantime, meantime, grab something from Stamp, maybe? Yeah, not sure. Okay. Well, thanks for tuning in to the stream. I think pretty productive studying for an exam on Wednesday. I was able to understand how the virtual memory system works a bit better and the different things you need to look out for. Also, performance, Amdahl's law, speed up, gigahertz, mean time till failure. I think those are all pretty helpful. TLB, translation look aside buffer. Bit confusing, but should be able to work that one out. Alright, thanks for tuning in to the stream. Gotta go get something to eat and be back soon. See you.